All right. Now we need to talk a little bit about design. And this is something we've already looked at this year, but let's revisit it. Remember, there are three types of design: designing by craft, designing by visualization, and designing by science. And ideally, the perfect design would encompass all of those. Your visualization, which is aesthetics, your craft, which is your craftsmanship and quality of design, and design by science, where it's supported by STEM principles. So when we're talking about designing by craft, this is what you can make with the materials you have on hand. A lot of times I see students that get stuck on this where they can't come up with a design unless they're looking at a pile of lumber and bolts and materials that they get to use. They can't envision outside of that. They need to see the materials in front of them before they can design. And you need to break away from that bad habit. Design by visualization is where you have in your head how you think it's supposed to look, and you have it all worked out ahead of time, even though you may not have the materials and you may not have thought about how it's going to work as far as STEM principles. So this is visualization. And then designing by science is where you actually apply your STEM principles. In this case, not just the visualization, but also looking how stress and strain will affect your design. This is a really good example. So take a simple example of a stool. You can think about how weight is going to be applied to the stool, how that force is distributed through the legs to the ground, how the ground is going to push up on the stool, how you have this ring which is going to keep the legs in place using tension, how that ring is attached with screws, and how you have to think about shear for that fastener. I got to help assemble some chairs for a sound booth, and someone put the rings on upside down for the mount, so the screws were on top instead of the underneath, coming from underneath. And what it meant is that instead of when people stand on top of the ring, it pushes down onto the frame held in place by the screw. When you put that upside down, now all the weight is held only by the screw, and so it was not going to be very sturdy, nor would it last very long. So that's just placement of things can make a really big difference. You have some STEM principles over here. We have stress, which is related to pressure, which is a force and divided by the area. So you could talk about the stress or pressure here, or again going through the legs. You also have the stress and strain curves for the metal. You know, where's it going to break, how much can it sustain until it passes that point, that yield point here, and fails. So these are the kinds of things you need to be thinking about for your design of your solutions. Anthropometrics, this is also the idea of ergonomics, is thinking about how your device is going to work when being used by people. They have some examples of this. They have some averages here and some averages here, and one of the things to realize is that there is no such thing as a perfectly average person. It is, when the military looked at this, they measured thousands of people, and they said this is the average size of a soldier, and then they went back and checked those measurements, and not one single soldier was average on all of those measurements. So they were always atypical at some point. So, but it does give you a place to work from. So when you look at a hairdryer, the grip here is designed to fit in the hands of most people, and the cord for it is designed to be used in most bathrooms. So that's how they thought about that design. And there's a lot of thought that goes into ergonomic workstation design. This one doesn't work for me. I've spent so much time at a computer, I can't have my screen this low. I have to have my line of sight more up here, so, or I will have pain in the neck. But so that's just an example of thinking about anthropometry or ergonomics. So now it's going to be your turn to go through and define your parameters and find those intersections with physics so you can come up with testable criteria. This is just a real short form. I want yours to be much more organized than this. So if you have some parameters like this, it has to go faster than 40 miles an hour. Then you've got your velocity formula. It has to be able to stop a 400-pound load. Now you're looking at stress, which is force divided by area, and it has to be comfortable for human use. So now you're looking at anthropometric data to understand if it's the right size for a typical person or your target audience. If it's to be used by children or women or men, those numbers may all be different. And then when you're looking at cost, if you set a cost limit, then you're looking at cost analysis and bill of materials, and it has to be scratch resistant. So now you're looking at hardness testing and that sort of thing. So that's an example of what we want to do. I want the format to be much cleaner than this when you do this assignment.